Thank you.
Yeah. Shall we start?
Yes, yes.
Okay. Next guy, Jongbaek Song from here. Title is Integral Cohomology for Coordination Toric.
Okay. Can you hear me?
Yes.
Hey. First of all, I'm very sorry that I could not attend this workshop in person. I was really looking forward to seeing all my colleagues in Japan, but I'm so sad that eventually I could not make it. So, and even so, I really appreciate the organizers for giving me this opportunity, online opportunity, to introduce my recent joint work with Xin Fu in Bimsa, China, and Larry So in Western University, Canada. So I'm going to talk about the integral cohomology ring of four-dimensional toric orbital. Okay, so okay, as an introduction of my talk, I'd like to begin with a simple basic definition of the intersection form in the theory of four-dimensional manifolds. So if you have a closed-oriented four-manifold, then you can think of certain symmetric bilinear form from the product of H2 to Z, given by if you have two cohomology classes A and B, then you can think of certain integer obtained by the cup product of A and B together with the natural pairing together with the fundamental homology class. Okay. So if you specify certain basis in this cohomology, like U1, UN, then this intersection form can be represented by certain matrix, square matrix, like the UI cup product UJ, and then pairing with the fundamental class is the entry of this my square matrix. Okay, just a basic linear algebra. So I want to look at the case where my M is a toric manifold or toric orbifold. In other words, M can be defined by some characteristic data, which we call this characteristic pair, P and lambda. Okay. For those of you who are not familiar with this characteristic pair, let's just wait for a couple of minutes. I will come to this definition in a minute. But whatever the definition is, toric manifold or orbifold this is certain topological space can be defined out of certain combinatorial nature, so called characteristic pair. So I want to express this square matrix, the matrix presentation of some sort of intersection form in terms of this combinatorial data. Okay. So probably this kind of question is the central question in toric topology, probably. So we have a toric manifold or orbifold, or in general, if we have a toric variety, then we can think of a bunch of topological or algebraic invariants. Then how to interpret, how to read off these invariants out of this combinatorial data. So that's kind of central question in toric topology. So I'm going to answer this question. So not just want to, I will express this matrix in terms of the characteristic pair, okay? So here is our theorem. We are writing this paper, writing is almost over. So the paper will be uploaded we will upload this paper on the archive very soon, I expect so. So think about a characteristic pair. Since I'm going to consider the real four-dimensional toric orbifold. So in other words, toric surface in the language of toric variety. So my polygon, the characteristic pair is it consists of the polygon together with the characteristic function. So I'm going to take a n+2 bond, but technically let me consider n+2 bond. And then my characteristic function is the assignment on each facet, in this case, edges. And then I'm going to assign two-dimensional vectors, so A1, B1, and AI, BI, AN, BN. And then here is a small assumption like En+1 goes to 1, 0, and En+2 goes to 0, 1. So in literature, sometimes this is called a smooth vertex, okay? Here are some remarks. So in the language of fans, in the toric variety, this characteristic pair can be represented by this fan data. So first you think of the 1, 0, 0, 1, you fix these two vectors, and then you think of a bunch of other rays. Okay. And also, second remark is, in general, whatever the toric variety is, whatever the toric surface is, each cohomology group is given by, in degree 0 and 4, it is Z, and this is simply connected in degree 1. And in degree 2, it is a free of rank n. N means the number of edges minus 2, okay? And in H3, there is a torsion, right? But if you assume the smooth vertex, the existence of smooth vertex, this implies that this torsion is trivial. Okay, this is not if and only if. The smooth vertex implies this one, but not the other way around. But anyway, smooth vertex implies that this is torsion free. So probably in the language of the notion of the Anton's talk in the first speaker, we can say that this is equivariantly formal toric orbifold, okay, integrally. So our conclusion is, whenever you have this kind of combinatorial data, right, then you can. So there is a nice additive basis U1 UN in H2 and a generator V in H4, such that the cup product UI and UJ can be a multiple of this degree 4 generator, and then my constant is AIBJ. Okay. So in terms of the matrix presentation, so if I have this map like cup product, this cup product map, then this cup product representation with respect to my basis U1 UN in degree 2, and then V is in degree 4, and then this matrix is given by in diagonal element are A1 B1, A2 B2, AN BN, and the off diagonal entries are A1 B2 A1 BN, and then this is a symmetric matrix. Okay. Okay, this is our theory. So it's kind of simple, and to us, this is really beautiful formula, I think. So for instance, let's think about this combinatorial data, like square and 1, 0, and 0, 1, and then -2, 1, and 1 and -2. For instance, in terms of the fan description, this is a 1, 0, 0, 1 here, and then these two vectors. Okay, so probably, I guess you will see this example in the talk of Hiraku Abe tomorrow, probably.
Yes.
And is that true, Hiraku?
Yes.
Okay, good.
Thank you.
So if you have this if you have this characteristic pair or fan, then there is a natural basis U1 and U2 in H2, and then V in H4, such that its coproduct representation is given by -2, -2. This is nothing but the product of these two entries, and then this 4 comes from -2 times this -2. Okay. Right. So. Okay, do you have any questions so far? Right, so let me explain. Yes.
I have a question. So you define the AI, DJ, the integers AI and DJ. Why you can write you take a cut product of UI and UJ evaluated on the fundamental class?
I'm sorry, I cannot. It's really difficult to recognize what you're saying.
Could you go back? Could you go back to the slide?
Yes.
So you defined AI, BJ, teachers
Yes.
such that how you define AI and BJ?
AI BJ is the characteristic. AI BI is a characteristic.
That's integer. I already defined. I'm sorry.
Yeah.
So
Yeah.
there is an additive basis.
Yes.
I see.
Yes.
Is it easy to see that there is such a basis?
Yes, that's exactly what I'm going to explain.
Okay, thank you.
Yes, thank you for the question. So from my side, I cannot see any of the audience. So please ask many questions so that I can check whether there are still audiences or not. So okay, so let me briefly introduce what these four-dimensional toric orbifolds are. Probably many of the audiences are familiar with the description, but let me briefly explain what this is. So I want to begin with my characteristic pair is a polygon n+2 gon, and the characteristic function is lambda is the characteristic function from the set of facets, in this case edges e1 en+2 to the two-dimensional lattice, such that whenever you have a vertex and the intersecting edges ei-1 and ei, then the corresponding characteristic vectors lambda of ei-1 and lambda ei, this must be linearly independent. Okay, so my toric orbifold can be constructed by the quotient space of the quotient space of this Cartesian product. So P times T2 modulo simulation. So in general, in order to explain this equivalent relation, I need to explain a little more notations, but luckily for four-dimensional case, there's a nice pictorial description like this. For instance, first you think about the Cartesian product of this just a polygon together with just a two-dimensional tori like this. Everywhere we have a torus, and then there's a equivalent relation. So the way how I do is first, if you think about this EI here, let me use some other color. So if you think about this EI, and then this is a T2, and then there is a natural circle subgroup generated by lambda of EI, because lambda of EI is a two-dimensional vector. So we can think of the circle subgroup corresponding to this direction, that particular direction. So my equivalent relation here is collecting this circle subgroup from this two-dimensional torus. So eventually, taking quotient, this surjective map is like collapsing the circle subgroup out of this two-dimensional torus. And then similarly, we do the same process for other tori. like this. And then accordingly, this vertex, so we are collapsing two different directional circle subgroup, lambda generated by lambda EI minus 1 and lambda EI. And then this, because this is the linearly independent, so eventually we collapse entire two-dimensional torus. So here we have just a vertex, just a 1 point. Okay, so this is just a pictorial description of this constructive definition of toric orbifold, four-dimensional toric orbifold. And then what is good for this picture is, if you look at this local neighborhood here, for instance, this yellow region, and this yellow region is locally look like this region times T2 modulo this relation. And then you can naturally compare this part together with the natural presentation of C2 by R2 positive times T2 modulo the standard relation, which means the coordinate from R2 positive represent the distance from the origin, and then coordinate from T2 corresponds to the angle coordinate. And then there is a natural endomorphism. There's an endomorphism of T2 given by the exponential of these two data, right? Okay. So since this lambda EI minus 1 and lambda EI, this is a linearly independent. It's not base, it may not be a basis. This is a linearly independent. So it has a finite corner. Okay. So this is the way how we look at this local neighborhood is look like C2 modulo some finite group action. So this G is exactly the corner of this exponential map. And then this C2 modulo finite group can be understood as a cone of this three-dimensional sphere modulo finite group action. Okay. So for instance, this boundary region corresponds to the sphere quotient finite group, and then we can take a cone of this area. Okay. And also, one small remark is, if this lambda EI minus 1 and lambda EI, this is a G basis. If this form a basis, then this group G is trivial. Okay. So this picture gives us a co-fibration sequence, like because there is a so there is an attaching map from S3 modulo finite group, and then remember that at each edge, at each point in this edge, there is a circle, and then this is a point. So at each edge, we have just a sphere. So we have a bunch of wedge of two spheres, and then there is a natural map from a point in this sphere quotient finite group to some point in the sphere. Okay. And also, we can think of this toric orbifold as a co-fiber of this attaching map. Okay, so this is a special topological structure, especially we can get from the four-dimensional toric orbifold. Right? Okay. So since we are interested in the cohomology ring structure, let me briefly summarize what is known for the integral cohomology ring of toric orbifold. So probably this is this is one of the famous results in toric topology and geometry. So a long time ago, Danilov and Yukevich, they proved that for a smooth toric manifold case of complex dimension n, not just a two-dimension, in arbitrary dimension, its equivariant cohomology ring is isomorphic to the Sani-Reisner ring, which is a truncated polynomial ring. So polynomial with variables corresponding to each of these facets, and then we have an idea generated by scale-free monomials like this. This monomial corresponds to the bunch of facets intersecting, non-intersecting each other. And this ordinary cohomology ring is the Stanley-Reisner ring modulo some linear relation. Okay, this is just a collapsing H star BT algebra structure somehow. So let me write down, for simplicity, let me write down this idea to be, what is the usual notation? This probably I, this is probably J, okay? And if you come to the category of toric orbifold, in 2017, Tony and Showman and I, we proved that for toric orbifold with vanishing odd degree cohomology ring groups, like equivariantly formal toric orbifold, then equivariant cohomology ring is isomorphic to so-called weighted Stanley-Weisner ring, which is some certain subring of the Stanley-Weisner ring. And also, the singular cohomology ring is isomorphic to the weighted Stanley-Weisner ring modulo the same linear idea. Okay. So for simplicity, let me write down this weighted Stanley-Weisner ring modulo linear relation by WSR bar of P lambda, just for simplicity. Okay. Here are some remarks about this weighted Stanley-Weisner ring. So remember, there's a Stanley-Weisner ring. Usual Stanley-Weisner ring is generated by degree 2 element, but its subring weighted Stanley-Weisner ring is not generated by degree 2 element. And then secondly, somehow we can describe the element. This is more like a GKM theory. So we can describe some element in the GKM cohomology, but somehow from the GKM description, it is not easy to find the minimal set of generators for each degree. So similarly, this weighted Stanley-Weisner ring, finding minimal set of generators for each degree of weighted Stanley-Weisner ring or this weighted Stanley, the WSR bar modular linear relation, it requires some case-by-case very tedious computation. This is kind of doable, but it requires many works. Okay, for instance, let's think about the characteristic pair like 1, 0, 0, 1, and AB. So this is the characteristic pair for the weighted projective space with weight A and D. And then weighted Stanley-Weisner ring is a subring of the Stanley-Weisner ring with variable, let's say x1, x2, and x3. So, okay, so to be more precise, this is, according to our previous notation, this is E1, and this is E2, and this is E3. Okay, so remember that I always put 1, 0, and 0, 1 as my last index, last two indices. After some hand computation, we can see that the degree 2 part of this weighted Stanley-Weisner ring is generated by these three elements, and the weighted Stanley-Weisner ring of degree 4 part is generated by some sort of this element. And then after taking this idea, portion out by this idea, the singular cohomology ring is generated by 1 in degree 0, and we can take this one as a degree 2 generator, and this one to be the degree 4 generator. Okay, so because everything is natural subring of the Stanley-Weisner ring, product structure is induced from the structure of the Stanley-Weisner ring. So AB x1 square is this one, and then modulo idea J, we can see that this is AB times x2, x3 degree 4 generator. Here is some multiple divisibility, right? So this is another way of looking at the product structure of the weighted projective space. Right. So on the other hand, recall that we have this co-fibration structure. Okay. With this, and then since we are assuming that P and lambda has a smooth vertex, we can take that vertex as my cone vertex, so that we have this S3 here. We do not have any finite group quotient here. So in this case, this co-fibration structure gives us a certain natural cell structure of xp lambda, right? So in cohomology degree 2, there is a basis, cellular, so some sort of cellular basis, U1, UN, corresponding to the two cells in each of these S two-dimensional sphere in the middle, right? And then in degree 4 generator, there is a generator corresponding to this S3, the generator for H3 over S3. And then connecting homomorphism gives me the generator for H4 of this co-fiber, okay, in algebraic quality. So we have this generator corresponding to these two-dimensional spheres and S3, some sort of, it has a natural, a nice topological nature, right? So let me summarize the situation so far. So far, we have defined two different types of bases for the same homology ring. One is the WSR basis, and the other one is cellular basis. Each of these two bases has an advantage and disadvantage. So one is the element, the presentation coming from this weighted semi-regional ring. It is really easy to see the product structure because this is nothing but the polynomial computation. But remember that it describes some elements, but it is hard to find the basis. We can calculate the generators, which may not be minimal number of generators. And then in order to extract the basis out of these many generators, it requires some computation. However, if you have a cellular basis, like in number 3 item number 3, it is easy to get a basis because it has a natural, it is induced from the natural cell structure, okay? However, their product structure is not obvious to see. What is the product of UI and UJ? What is the divisibility of UI UJ with respect to this degree 4 generator, right? So how to associate these two in order to take the nice part of these two? So how to associate these two? So this is our main question. Okay. So question, and then from now on, I'm going to explain how we make this association. Are there any questions so far? Okay, a long time ago, one speaker, one professor told me that when you give an online talk and then when you happen to say that, are there any questions so far? Then she or he told me that you have to count 5 or 10 seconds. So in order to give time to prepare to ask some questions. So, okay, let me count 5, 4, 3, 2. Okay, here we go. So the easiest example, now I want to associate these two bases, okay? The easiest example is probably the CP2. So here are two different ways of understanding two-dimensional projective space. One is to think about this characteristic pair, 1, 0, 0, 1, and 1, and 1, like this, okay? And then our standard, the well-known result by Danilov Yukevich, we can think of this cohomology ring is isomorphic to this truncated polynomial ring. And then if we express this polynomial ring degree by degree, then in degree 0 we have Z, and degree 1 and degree 2 we have this is a rank 1 generated by X1. Okay, I'm writing this bracket in order to express this is an element after taking modulo, after taking the ideal J linear relation. And degree 4, we can take a generator X2 and X3, and its product structure is X1 square is equal to X2 and X3. Okay, so because the linear relation is what? So in this case, because this is x1 and this is x2 and this is x3. So x1 plus x2 is equal to 0 and x1 plus x3 is equal to 0. So x1 squared is naturally x2 and x3 in this case. On the other hand, we have this co-vibration structure. So the cohomology ring has a generated by U and V. So remember the U comes from S2 and V comes from S3. Somehow it has a topological nature. So this is as a group, right? But what is good for this example is rank 1, H2, the rank of H2 and rank of H4, sorry, there's a typo. This is rank 4, okay? So rank 2 and rank 4, this H2, rank of H2 and rank of H4, these are 1. So there's no way to think about the linear combination of the other presentation, right? So we may regard this U corresponds to this generator and the V corresponds to this generator. Of course, we can think of the sign convention, but let me just skip that little complicated part. But let's just assume that we can regard this U corresponds to this element, V corresponds, U corresponds to this element, and V corresponds to this element with some appropriate choice of orientations of S2 and S3. Okay, the sign corresponds to the orientation of S2 and S3. Okay, so there's no way to think about the linear combination of the other presentation. Okay, so this is the easiest example to see the association of the standard presentation and cellular presentation. All right. So in order to consider the general characteristic pair P lambda, and then temporarily, let's assume that there's a smooth vortex. Okay? And then we want to make use of the CP2 example computation by the following picture. Okay, so there's a long way to go from this general characteristic pair to the characteristic pair for the CP2. Okay, so this is just a combinatorial procedure of getting this pair from this pair, this general pair. Okay, so first you think about the edge contraction. Okay, so let me draw some picture. Okay, let me use this technology. So my edge contraction means I'm just looking at this edge and this edge and this edge to get a triangle. Okay, and then I'm going to collapse all the other unnecessary edges like this part to this vertex and this part to this vertex. Okay, some combinatorial procedure. And then in order to get this the characteristic pair for the just projective space, ordinary projective space, I want to rescale. I want to change this AI BI into 1 and 1. Okay, there's no mathematics here, just there's some rule. Okay, so the combinatorial rule, like some edge contraction and then changing this vector into this one. But in order to use this kind of combinatorial description at the level of toric variety or cohomology, we need some proper notion of morphism at the level of toric variety or its pullback at the level of cohomology. Right. So let me briefly explain some morphism corresponding to this combinatorial procedure. Right. So first, let's think about some two characteristic pairs, P lambda and P prime and lambda prime. So these are characteristic pairs with dimension d-dimensional and d prime dimensional. It doesn't need to have the same dimension. Okay? And then think about a map, like phi1 and phi2 from P times TD and then P prime times T, just a product map, like X goes to phi1 and X, and then T goes to phi2 of T. Okay? And then we call this kind of map as a compatible pair if we satisfy certain condition. The condition is for this phi1 map, phi1 is the map from P to P prime. So whenever you have a face over P, then there should be a face E prime of P prime such that its image should be a subset of EI, E prime, sorry. This is typing, sorry. I checked many times, but this, yes, anyway. So the condition is if you have a face, whenever you have a face of the domain, then its image of phi1 should be a subset of certain face of P prime. Okay, and then the condition for the second map phi2, if you have remember that whenever you have a face E, then this is the intersection of a bunch of facets, and then each facet has a characteristic vector, so that we have a subtorus generated by those characteristic vectors. So that we denote by PE. And then this subtorus, the image of this subtorus should be a subgroup of TE prime, this one. Okay. I guess this condition, it requires some time to feel what this condition means. But in summary, in short, this condition implies that if we have this compatible pair, in other words, this product map satisfying this condition, okay, then this product map naturally descends to the level of toric variety, this quotient space, this toric variety. Okay, so this condition guarantees that this product map descends to this level. Okay. So our definition of toric morphism is the morphism induced from this compatible pair. Okay, we call this map a toric morphism, right? So here are two examples. Before that, let me introduce this diagram first. So for not only this toric morphism, if you have this toric morphism, then remember that we have when you have this cohomology ring, this is isomorphic to the standing regional ring, weight the standing regional ring modulo the linear relation, which we denoted by WSR bar of P lambda. And then there's an isomorphism, right? So whenever you have a toric morphism, X of psi1, psi2 corresponding to this compatible pair, then you can define a map at the level of weighted standing regional ring by this diagram, right? So we can define this WSR bar psi1 and psi2. Okay. Right. So let me show you some examples. So let's begin with the characteristic pair, just arbitrary characteristic pair, something like this. And then think about another characteristic pair, P prime and lambda prime. And I'm going to change the characteristic vector by multiplying this matrix. And then take a primitive. Okay, so to be more precise, okay, not directly. First we take a product and then take a primitive. Okay, because multiplying this matrix, the resulting vector may not be primitive, and then so that we can take a primitive. And then remember that taking primitive vector does not affect anything about the underlying topological space of the corresponding toric variety. So it's just a matter of direction, right? So something like this. And then since I am taking product of diagonal BI and AI here, so this edge becomes AI, BI, and BI, AI. And then taking primitive vector of this guy is going to be 1 and 1, right? So this is the procedure that I'm changing AI, BI into 1 and 1. And accordingly, there are some, the other vectors will be changed. So P lambda, so now I have P lambda and P prime lambda prime, right? Then, and then with respect to these two characteristic pairs, I can think of a comparable pair like psi1 and psi2 given by the first map is identity on the polygon, and the sigma I is given by this matrix. Okay. So probably if you are familiar with the language of fans, then this rescaling morphism corresponds to some sort of lattice subdivision. For instance, if you have 1, 2 in a standard lattice, like this vector in a standard lattice, then we can think of them certain subdivision of this lattice, like subdividing here in the middle, like this, right? Then this one, as an element, as a direction of in a vector space, it has the same direction, but as an element in a lattice, it becomes 1, 1 in subdivided lattice, right? So 1, 1, right? So it corresponds to some. There is a corresponding language in the level in the language of corresponding notion in the language of fans, the lattice subdivision. So, so remember that whenever we have a comparable pair, then we can define a toric morphism. And then whenever we have a toric morphism, we can define a map at the level of weighted standardized beam. Okay, so the map from the weighted standardized beam of P lambda, what was something is wrong? So which one is prime? P prime lambda prime. So because our comparable pair was from P times T, so yeah, P lambda and then P prime and lambda prime, right? So the cohomology is a contravariant. Okay, so our first lemma is the map weighted standardized beam corresponding to weighted standardized map corresponding to this comparable pair from the weighted standardized ring of P prime lambda prime to the weighted standardized ring of P and lambda. Whenever you have a polynomial like corresponding to the variable x1, xn plus 2, and it goes to some same format of the polynomial but changing some variables. And then this variable is given by when j is equal to I, then ai, bi, xi, just some details, but ai, bi, xi, when this j, the index j is the same index when same index that I took for this rescaling. And then for n plus 1, we have bi times xn plus 1, and for n plus 2, we have ai times xn plus 2, and in the other indices, we have this one, another type of xj. Okay. Some details, but there's some computational result at in the level of weighted standardized. Okay. My second example is the edge contraction. So remember that edge contraction is nothing but the collecting all the edges except for 3 edges that I want to look at. For instance, in this case, I'm collecting all the edges, these edges and these edges to this vertex and this vertex, right? So eventually, I only have this and this and this as edges in this triangle. Okay, and then my comparable pair is the the edge contraction at the level of polygon, getting this triangle out of this P, and then identity map at the level of in the map of torus, two-dimensional torus. And then similarly, since we have this compatible pair, we can think about the toric morphism X of psi1 and psi2, and then we can think of by the commutative diagram, which I showed you just several minutes ago. We have this map at the level of weighted Stanley-Reisner-Wing, and weighted Stanley-Reisner-Wing, the map is given by like this. Remember that, okay, so I was too sloppy about this explanation, but remember that this pair, we have this weighted Stanley-Reisner-Wing has a generator, was generated by this element and this element in degree 2 and degree 4, right? So these are generators for degree 2 and degree 4. And so it is enough to just look at these two elements, how it goes to the target space. So our lemma, the computational lemma says that this element goes to some sort of this complicated formula, and then this element goes to this one. Okay. So what I want for you to look at is this x2 and x3 corresponds to these two edges, to the product of these two elements, and the yn plus and yn plus 2 is to somehow the product of these two elements. This is this part is easy, but degree 2 part is rather complicated, right? All right, so this is kind of preliminary for the proof of our main theorem, but so let me just revisit our main result again. So the theorem is what? So suppose we have a characteristic pair, okay, something like this, and then characteristic function is a bunch of vectors, a1, b1, ai, bi, then a and b, and then we assume that there is a smooth vertex, 1, 0, and 0, 1. Then the claim is there's an additive basis u1 and un, and generator v in degree 4 such that the cup, and then with respect to this basis, the cup product structure is easily understood just by looking at the characteristic vectors. Right? So ui times uj is nothing but a, I, bj times v. So these numbers appeared in some place in this characteristic vector. Okay. So, all right. So here is the idea, brief sketch of the proof. It consists of several steps, but the first step is to look at the triangle example very, very carefully. So I already explained this example several times, right? So if we have this triangle example, then and then we have this weighted Stanley-Reisner ring for this pair, and this is a subring of the usual Stanley-Reisner ring, and then we define a basis u and v, right? So remember that this is a weighted projective space. Its rank in degree 2 cohomology is 1, and rank of degree 4 cohomology is 1. So similarly for the usual projective space, I mean the easiest example that I introduced several minutes ago, there's no way to think about the linear combination, just a plus minus association with this cellular basis u and v, and the Stanley-Reisner basis generator of these two elements. So let's define this u and v such that, I mean, define means some orientation things. It involves some orientation, plus minus sign. But anyway, we have this u and v. We can define this u and v such that it maps to degree 2 generator a, b, x1, and degree 4 generator v goes to x2 and x3. Then u square, so we can calculate the product structure u square by at the level and in the world of this Stanley-Reisner ring, because it is easy to product by just polynomial computation, right? So this one, so u square is this one, and then this element is AB times degree 4 generator as above, and then the phi inverse of x2, x3 is the degree 4 generator, so this is AB times B, right? So this is the precise computation of the case of triangle example. And step 2, so from step 2 and step 3, we think of the general toric orbifold having the smooth vortex assumption. So remember that we want to, the goal is to look at this matrix presentation, Cij, okay? So first we look at the diagonal entries of this product, the coproduct representation, and step 3 will be the computation of this off diagonal entry. Okay, so for this diagonal entries, we use this edge contraction from the arbitrary characteristic pair to the characteristic pair of the triangle. So its topological interpretation of this edge contraction morphism is some kind of, so remember that we have this co-fibration structure. And then this edge contraction is nothing but collapsing all the other spheres, 2 spheres, except for the correct 2 spheres corresponding to the remaining edges. So probably it's better to say this ith 2 sphere corresponding to this part. Okay? So you pinch all the other 2 spheres so that we have another attaching map so that the resulting co-fiber is going to be the 2-dimensional weighted projective space. So we have a map from the toric orbifold, which we want to look at, to the weighted projective space. And then there's a toric morphism coming from the comparable pair corresponding to this edge contraction together with the identity map on the 2-dimensional torus. Okay, and then it's pulled back at the level of cohomology here. Then this U goes to, U means the basis in which we defined in the step 1. U goes to UI, the cellular basis. We can define the cellular basis in UI by the image of this one, by this morphism. And then remember that this U goes to this element as an element in this weighted standing diagonal ring. So finally, we can take the product of the scale of UI by the computation at the level of this triangle. So UI to the square is just we just pull back of this U square in the triangle, the cohomology of weighted projective space, and then we continue the computation like this, and then finally we have AI BI times V. Okay. And what was this V? So V is the element. Remember that we have another element in this V in H4 of this one, and it goes to here by V. Okay. For the computation of off diagonal entries, so we use this diagram, right? So first we think of the arbitrary toric, the characteristic pair of dimension 2, and then the off diagonal entry is just a multiplication of UI and UJ. So we just, in order to make the computation simple, we only look at this ith edge and jth edge, and then we collapse all the other edges like this vertex. And then in the middle, we have this vertex, and then all these edges to this vertex, so that we have we can think of another edge contraction morphism collapse, which preserve this and ith edge and jth edge. Like the target space will be the characteristic pair for the of the square. Okay. And then from this square, we can think of more edge contraction to get a triangle examples, which are our favorite spaces. And this combinatorial procedure corresponds to this topological co-fibration diagrams. So first we think of this co-fibration sequence, and we just pinch all the other two spheres except for I's two sphere and J's two sphere. And then there's another toric variety, four-dimensional toric orbifold corresponding to this characteristic pair. And then this two direction gives me another other two co-fibration structure coming from these two by just pinching Sj or pinching S2 of I. Okay, so we have this two weighted projective spaces. So our lemma is, it looks a little complicated, but this kind of these two pictures, at the level of cohomology, we can get this parallel picture of the cohomology rings. So we have this. So this left-hand side is exactly the cohomology, and then we can send this picture to the world of weighted Stanley Reisner ring here, right? So, and then we know all the information, what is happening at the level of this triangle, right? And then our lemma is showing that if you have this cellular basis at the level of this triangle example, then remember we know this part, right? And then this lemma claims that this edge break element goes to this element and this element. And if we have another element corresponding to the index J, then it goes to this element and this element. Okay, so we can think of the product of these two elements at the level of we can think of the product of these two elements by looking at these elements. Okay, so the conclusion is Ui and Uj in the as an element of the cohomology of the toric orbifold corresponding to the square characteristic pair, then we can take a product. Sorry. We can take a product at the level of weighted Stanley Reisner ring like this, and it is easy, just a polynomial computation again, and then it goes to AIBJ, so that we have this AIBJ times the degree 4 generator. And then finally, all this square computation at the level of scale goes to the level of the it gives the one off diagonal entry of the cut product structure of the given toric orbifold, right? So just a parallel computation coming from this square example. So we have this one, right? This is in x of square, and then this is in x of p lambda, right? Okay. This is just a brief. I omitted many details behind this computation, but this is more or less, this is just a brief sketch of the proof. For instance, let me finalize my talk by showing you this example again. Okay, so if you have this toric orbifold corresponding to this Cartan matrix, maybe Haku will introduce this example again, but anyway, its cohomology is generated by Z in degree 0 and 4, and then Z2 in degree 2, and then it vanishes, O degree cohomology group vanishes. So there is a natural basis UN and U1 and U2 just by, and then cut product structure can be obtained just by looking at the characteristic vectors, right? So that is this is our main result, right? So thank you for your attention.
Any questions or comments?
I have a question. Can you hear my voice from there?
Yes, but if you can say a little more loud, then it's gonna be better.
With microphone.
Oh yeah, this is good.
Okay. So I think one of the advantages of your main theorem is to compare the cohomology when two cohomologies are same. So I want to know in your class cohomological rigidity holds.
Well, okay, rigidity requires several things. One is whether you are requiring the homeomorphism classification or diffeomorphic as an orbifold classification. But our previous paper in Shin-Fu and Letty, we proved that cohomological rigidity problem for the homotopy classification is true for this class of orbifold.
So
I mean, if you have a two toric orbifold, 4-dimensional toric orbifold having the smooth vortex, for instance, then if those two orbifolds has a isomorphic homology rings, then they are homotopy equivalent. Somehow, yeah. So this is what we know, but we are not so sure. So far, I'm not so sure how to attack the homeomorphism classification of the underlying topological spaces.
I see. Thank you very much.
Thank you for the question.
Hi, Jongbaek. Can you
Hi.
hear me?
Yes.
Yeah, thank you very much for nice talk. And I have a question. And your UI, so in terms of cycle, can you explain the UI in terms of cycle?
In terms of what?
Cycle. So second homology. As you said, the space is a wedge of S2 and attached to 4-dimensional cell. So can you like explain that your UI UI homology class, but I'm wondering whether you can explain the UI in terms of homology class, a cycle.
Cycle. In terms of, well, okay, yes, UI is the okay. UI is nothing but the because this co-fibration structure gives us a natural cell structure. So we can think of the cellular homology. So this UI is the dual of two cells of each two sphere. I'm not so sure whether this answers your question, but
So that S2, where does it come from? That S2?
Yeah, so we have this co-fibration, right?
Yeah, but you started with n+2 gon.
Yes.
So if the n+2, if you look at the edges of n+2 gon, you have n+2 edges. So from there,
yes.
From there, you naturally get n+2 S2.
Yeah, we have n+2 S2s. But
Yeah.
however, if you pick up one vertex like this,
Yes.
then this local neighborhood, we have this part is S3 modulus and finite group.
Yes.
We have remaining n edges.
Yes.
Right. So this n edges corresponds to n many two spheres.
Okay, so, but then sounds strange because if S2 are disjoint, then there is no intersection. But your UI cup product.
It's a wedge. Sorry, it's a wedge. It's not disjoint union. So when we shrink all the other edges to a point, it gives us a wedge of n copy of two-dimensional spheres.
Yeah, wedges of S2.
So each of the yes.
Yes, so here we have this picture.
Oh yeah. Then how do you get the wedge of S2?
Okay, again, I'm not so sure, but again, here we have this picture.
Yes.
But up to homotopy, we can think of this one as this picture.
Okay, so
Yes, not circle, but think of the spheres, two-dimensional spheres.
Two spheres above here. If they are disjoint,
Mhm.
then they have no intersection.
They have
I wonder
intersection.
why UI cup product UJ is
Right, so it's not like some intersection in the algebraic geometry, I think.
I'm sorry.
So it's not the intersection. So the coproduct is not the intersection of two submanifolds, but here we have the coproduct. The product structure of this coming from this co-fibration structure is the Whitehead product of corresponding two spheres.
Yeah.
So this coproduct structure is not coming from the intersection is not coming from the intersection of some two spheres.
Geometrical intersection. Geometrical cup product is just
It's not geometric intersection. It's not. So every computation comes after we deform the space up to homotopy equivalent somehow.
Other question or comment? We could already speak again.
Okay, thank you.
So next we will start for 20.